I just wait one more. Okay, so happy to introduce Georg Schmidt, and he's going to be talking about photon magnon coupling and superconducting resonators. Well, 1 hour, 45 minutes plus 15 minutes per questions, but we're like very flexible. So yeah, please take it away.
Thank you. I was told 50 minutes, so I will try to stick to 50 minutes. So first of all, I would like to thank the organizers for getting this event here. It's really nice, although I missed the first week, but I'm enjoying the second one. I hope you knew what you were doing when you invited me here, because I will not talk a lot about quantum, but I think I can still contribute a little bit. And I must also say that unfortunately, although I'm here since Saturday, last week a delayed jet lag hit me. So if I start to show some decoherence during the talk, you maybe just ask some questions to get me back on track. But I hope that things will work out fine. And also, I discussed via email with Carlos, and we agreed that I would start with a brief tutorial. And I think so I hope for some of you this will be completely clear what I'll be saying, but some time ago I tried to break down actually the theory of strong coupling so that I could finally understand it, because I don't like equations. I always want a picture behind the equation that I can understand, and maybe my picture may be interesting for you. If not, just enjoy the talk, but later on there will also be different stuff. So now I have to see, yeah, it switches. So this is the group behind all this, and some of you may know this guy, Seth Kaufman. So he was with Zeek before, and now he is really enjoying the work in this group. And also this girl here, she left meanwhile, Stephanie Lake. She was also with Zeek, so it's a constant source of good people and a good part of the collaboration. But as you see, also others have contributed to this work. And there are also external collaborators, so there was some contribution from the optics group, from Georg Woltersdorf and Ruven Dreyer. Then Hans, who is here, did some work on the mechanical oscillations, which I will only briefly mention. Then some work from CIA and Spintech, Olivier Klein and Grégoire de Lubin. And then we have Michael Flatze and Daniel Pühl. They did a lot of theory on the strong coupling, and we have some funding by the German Research Foundation and by the European Union in the Palantiri project. That's what Hans mentioned yesterday, where we try to couple from microwave photons to light photons via phonons and magnons. Okay, so what I will talk about, I will give you a brief introduction. In principle, after the talk yesterday, I can mostly skip it, but I will just go through it fast. Then I will give you a tutorial about strong coupling. Then I will show you some real stuff, and I will give another brief introduction on resonators, just because there are certain thoughts which are important to understand the final experiment, which I summarize here under some unreal stuff. It's a bit special, so these are new results, and I have no idea what we are seeing, and I would just ask you in the end whether you have any idea what we're seeing. Okay, but why are we doing all this? So coupling phenomena is basically about the coherent transfer of elementary excitations from one type of excitation to another. And for example, in communication, you want to transfer between microwaves and light, quantum information, qubit readout, transfer, storage of quantum information with single excitation quanta. And this requires the coupling of different kinds of oscillations. So you may have photons, microwave, light, phonons, and magnons that can mediate between those, and you will see, so all the experiments that we are doing are simply at too high temperature to approach the quantum limit, so we're not going below 1.5 Kelvin. A little bit about the state of the art. So it has been shown that you can couple qubits to magnons, but I guess this has also appeared already on some transparencies. Also, there's been shown that you can couple qubits to mechanical oscillators, so why not use magnons and magnetoelastic coupling? And this has already been shown yesterday that you can use the magnetoelastic coupling for interesting and high Q experiments. And it has also been demonstrated that you can couple magnons to phonons. So this is the group from the work from Hong Tang's group, from Shufeng Zhang. But the problem is that the Yeek resonators are typically macroscopic spheres, so 250 micron and not suitable for integration. I mean, Hans has gone down a little bit with this already to a smaller size. So what we need is we have one coherent elementary excitation, and we need a fast coherent transfer to another excitation, in our case, for example, photon to magnon. And the necessary prerequisites are that you want strong coupling, so that fast coherent energy transfer between two states. And for this, you need a large mode overlap, and you need a long-lived excitation with long decoherence times, longer than the energy transfer, and long enough also for further processing. So this is what you need. In principle, in the end, it's very simple. So you need strong coupling, and you need a very narrow line width. And here, normally there would be a longer part about the difference between line width and damping, but I will only briefly mention this because it is important. So Yeek is one very nice material. It's a ferromagnetic garnet, and it can have very low Gilbert damping, like 3 times 10 to the minus 5. From Zeke's talk yesterday, you heard that 3 times 10 to the minus 5 is really low. And also the resonance line width can be very small. Also, it's quite rigid and suitable for mechanical resonators, and here are Hans' results. So this is a cantilever that we fabricated. Look at the scale, so this is 2 micron. So it's roughly 2.5 micron long, and it has a nice resonance at about 13 megahertz, which is too low for typical magnon frequencies, but we can also make resonators which go to much higher frequencies. But this was a first test, and we saw something, and it seemed like a good start. But anyway, so what is important for the coupling? You need a long lifetime of the magnon state. And the question is, in principle, the lifetime is given by the damping, so 1 over 2 pi alpha at the resonance frequency. But the problem is you have inhomogeneous broadening. And this reduces, actually, if you think about it in detail, inhomogeneous broadening can mean that you have an inhomogeneous material which actually has different line positions in different part of the volume. These lines can be very narrow. So in principle, you have a lot of low damping material. But if the spread of the lines is big enough, you have a problem. So you can have 2 different problems. One problem is that these 2 regions are even coupled. Then it's clear that your lifetime is not what you would like it to be, but still it can be. If you look at the damping, basically you plot the line width over frequency, and if you plot this over frequency, you see all these lines as a big line, and this line is getting slightly wider, but it doesn't help you. So theoretically, you can have 0 damping. There is one publication with negative damping, but a huge line width. And so it just is the behavior of the different lines that you observe. So this is the worst case. The bad case is, oops, that was too fast. The bad case is if these regions are uncoupled, so that you indeed have regions with narrow line widths and different resonance frequencies. But again, this means you also want a large mode overlap for your experiment. And only a small part of your volume will be actually part of the experiment. So you can have longer lifetime, but you have less mode overlap. So this is also bad. So what you want to have is narrow line widths, full stop. There's a lot of discussion about this, but there are many people who agree, don't look at the damping, just look at the line widths. Okay. So now, let's talk about strong coupling. And as I said, I tried to break this down, and maybe you like the picture. So we're talking about 2 coupled oscillators, and a very useful example, because it's so easy to understand, is 2 coupled mechanical oscillators. So this is actually, these are the 2 mechanical oscillators, and this is the coupling between the 2. You have 2 springs, you have 2 masses which determine the resonance frequency, and you have the coupling in between. And the equations of motion are very simple. I will not go into detail, and you can look at the solution. You actually get these 2 omegas, and here you have this omega A and omega B. And you can actually see that here you have, for omega A, you have Ka plus kappa divided by Ma, and omega B, you have Kb plus kappa divided by Mb, and you have this coupling parameter G. And So omega plus minus omega minus is, so the two solutions, the difference is actually the coupling strength. But as I said, I don't like the math in this case. But note also that omega A and omega B both contain this kappa parameter. And now let's look what happens in this system. So because you all know this anti-crossing, which is a sign of strong coupling, and let's consider a system in which one of the oscillators remains at its frequency while the other one changes its spring constant. So one oscillator is here and the other one is there. And without coupling, the two curves cross. And with coupling, you find that this gap opens here. This is also described by the equations. And we have this anti-crossing or avoided crossing, but the question is what happens here and how can you explain this except for the math? And by the way, the size of this gap shows the strength of the coupling. So, and what is the nature of these two modes? And this is what actually what gave me the idea to use this picture was that I'm giving the solid state physics lecture every year. And there I'm also talking about the phonon modes. And there are these phonon modes of the optical. You have the optical phonons where the two sublattices are out of phase, and you have the acoustic phonons where the two sublattices are basically in phase. And how can you apply this here? You have these two coupled oscillators, and in most cases, so when you're looking here or here or here or there, only one oscillator is on resonance. That's what you have there. The other one follows, and it simply follows as a forced oscillation. And the rules for a forced oscillation are very simple. If the forcing oscillator is at a lower frequency, so for example down here you would have, so I simply can also say in principle this is the magnon line, this is the resonator line. In principle, if the magnon is at low frequency, but if the forcing oscillator is on resonance and at low frequency, then the force oscillator has a very small phase shift. It will just follow. You know, if you excite an oscillator below its resonance frequency, it just follows. Small amplitude. Same thing, by the way, here. Here, the resonator is on resonance and at a much lower frequency than the magnon, which would be up here. So if the forcing oscillator is at higher frequency, the forced oscillator has a phase shift of pi. You know this, above resonance frequency. It cannot follow, and you have a phase shift of pi. And it's like the small mass is oscillating very fast, and this one has a very small amplitude and is at opposite phase. And we now see that this line, at least at these two parts, has opposite phase, and this line at these two parts has zero phase shift. So they have identical phase. And the question is whether we can follow this until the center, because this is the interesting part. And when the two frequencies are degenerate, so when you have the two masses and the two spring constants identical, you have two eigenmodes. And the eigenmode 1 is that both oscillators are in phase, and you can still stick to the forced oscillation, so each oscillator is forcing the other one. So each has a phase shift of 90 degrees with respect to the other one, which can give you either 180 or 0. And if both oscillators are in phase, so 90 degree minus 90 degree with the same amplitude, so they are both oscillating back and forth, then this spring, the coupling, there's no deformation. So there's no, you see no deformation, and omega is just equal to k over m. They both are synchronous oscillators. The other state, up here, where you would expect 180 degree phase shift, they have 90 plus 90 with the same amplitude. Then you have them opposite phase, same frequency. But also in this case, so the difference here is this spring is now deformed. And so you have a different spring constant. In the end, omega is now k plus kappa divided by m. So you have two different eigenstates, two different eigenmodes of your oscillator. And actually, when we do our resonance experiment, it means, you know all these lines, it means that we're measuring these eigenmodes. And this was, for me, a very important insight, because eigenmodes, you know that Eigenmodes don't develop in time, and so these are the modes where actually no energy transfer is taking place. I mean, always when we're talking about strong coupling, we're talking about the energy transfer between different states, but here we don't have energy transfer. These eigenmodes are stable in time, and this is something that you have to keep in mind, that this is the only what you get out of your experiment is the information about this frequency. But you can also see that there was indeed the difference between the two was once the frequency was the square root of omega divided by of k divided by m, and the other one was square root of k plus kappa divided by m. So actually it's the kappa which determines basically the difference between the two frequencies. So, and only when you have a mixed state, so when you excite only one side, then you can have the energy transfer happening as at the coupling frequency, and then you observe this beating pattern between the two states. And it's easy to understand if you have a state like this and a state like this, you can have a superposition where one of the two is at 0 and the other one is moving. And from our picture, we now understand that this will develop into a state where this one is at 0 and the first one is moving. Okay, so now what else do we have? We have some damping that kicks in. So you get additional terms which are gamma A times x point A and gamma B times x point B. And we find that splitting simply gets smeared out by the resonance line broadening. And in order to distinguish the lines, it's necessary that G, that the coupling strength is bigger than the sum of the two line widths. Or in other words, G divided by gamma A divided by MA plus gamma B divided by MB is bigger than 1. This is, I can say, this is a satisfactory condition for strong coupling. So if you, and Hans has also mentioned this yesterday already. Another important parameter is the so-called cooperativity. This is G squared divided by the product of the two. And in the strong coupling regime, this is always bigger than 1. But it's not sufficient for strong coupling because you can easily imagine if you have one of the two very small, you can always have this bigger than 1. And, but the other line width can be very broad and it can completely kill your strong coupling because you still have a mode overlap. And in the end, if you look at it closely, you find that the first definition, the satisfactory definition, is that G is larger than the arithmetic mean of the two line widths. And the cooperativity means that the coupling strength, it compares it to the geometric mean of the two line widths. So just simple math behind it in the end. So now let's get down to business after you know what we're talking about. So our target is we want to investigate strong coupling of magnons with light, which I will not show here, but it has been done. Phonons, which I will also not show because we're not there yet, but we have some ideas how to get there. And microwaves. But this we want to do with high Q micromagnets because all these experiments that you see here, they have relatively large Higgs spheres. So relatively large means that 250 micron is nothing that you can integrate with 1,000,000 qubits. If you want 1,000,000 qubits to couple to Higgs oscillators, you need micron-sized Higgs oscillators. And yeah, if you want to couple to cavity photons, what is a good cavity size for the high cooperativity? You need a large overlap of the mode volume. And hollow cavities work nicely when you have these Higgs spheres, so then you have these large copper cavities, but they are way too big for micromagnets. So if you put a micromagnet inside, the mode overlap is simply too small. And what about superconducting resonators? And there we have already seen some examples from Hans, and certainly I'm citing his paper here from 2013. He had this kind of resonator and he put a Higgs film on top. But it's still pretty large. So lambda is in the range of centimeter if you are at 4 gigahertz. You can fold it together, then it becomes a bit smaller, but still it's relatively large. And in the end, one can also say you cannot get the resonator to micron size. Too bad. But you can still try to make it smaller. This is scalable only within limits. And There has been some demonstration of strong coupling for permalloy magnets down at least to 0.1 millimeter size. So here are two experiments, both from 2019. One was from the group of Axel Hoffmann, who unfortunately is not here anymore. And I'm very sorry that I missed his talk. Maybe he even referred to this experiment. But he could show strong coupling in this kind of resonator. I think this was his work. But another choice, which may be better, is the lumped element resonator that Hans mentioned yesterday, or the LC resonator, as I will call it. And here you have this simple picture. So he had a different design. Basically, you have a capacitance here, and you have your inductance here and there. And you have a feed line at the side, and I will come later to this. But a good picture about this is you just have two capacities, and you have these inductances here. And in this resonator, you can actually have two modes. They can be either like this, or they can be like this. And one of the modes has no field in the center, and the other one has a high field in the center. But I should also say you can also just cut away one side of it and it still works. Then you still have an LC resonator, but you only have one resonance. In some cases, this may even be more useful because you may have better access to the geometry. And you can concentrate the magnetic field around the inductive element. And as I will show, you can do this quite nicely. And there has also, from the Hoffmann group, there has been demonstration of coupling of a permalloy stripe with the LC resonator. But they didn't get to the strong coupling regime with this one. They only made it with, yep, sorry. That's actually Okay, sorry.
Sorry, that's Lucello's paper.
Sorry.
It's same time almost as Axel's paper, but this, yeah.
Okay. My mistake, I apologize. That I mixed it up. But anyway, so for these resonators, so both papers showed strong coupling, but only for the lambda half resonators, not for the lumped element resonator. And in this case, but the permalloy element was already pretty small. So this is microns, 40 times 2 micron times 10 nanometers. So it's pretty small. You have high cooperativity, but no strong coupling because permalloy has large line width. So now we started to work firstly by modifying this resonator slightly. We made it a bit more narrow here. This is work started by Philipp Geyer. And we first put a permalloy structure. I will briefly go to this. This was just the first try, but it gave us a hint for a later experiment. And here we see some simulations of the resonator. As I said, you have one mode where you have the field concentrated here and one mode where there's no field in the center. This is how the structure looks. We put it into our cryostat, and the setup was also developed thanks to Hans. So he gave us a lot of information how to do it, and he actually gave us also the design for our copper box. Q factor of the resonator is about 1,000 at a resonance frequency of 3.7 gigahertz. But this is not so important. We found we can have some coupling, not strong coupling, but we also found that we have to get the field in the right direction. Because then we only get the right resonance frequency. If we apply the field along this line, as you would normally do it, the resonance is too low to have any interaction with what we have. But that's not important here, because now we wanted to move towards YIG. And in this talk, this will be merely a sideline, but an important piece of information, because then you can see what we can do. Normally, nanopatterning of YIG is non-trivial. And the GGG substrates are pretty detrimental for low temperature measurements. So also, GGG substrates are completely unsuitable to make superconducting resonators. So the material is still superconducting, but the damping is so high that you don't see a resonance. So what we need is first of all, nanopatterned YIG somehow, and ideally, either without a substrate or on a substrate other than GGG. And this guy developed a nice technology that we're still using. Currently, Seth Kaufman is working on it. By using e-beam lithography and PLD and subsequent lift-off and annealing, we can make structures like this, which are freestanding and which are not in contact with a substrate. And here you can see some resonance modes that we have excited by a coplanar waveguide, and which we have imaged with time-resolved MOG. So you can see you have a lot of standing waves, standing magnons in there. So, and this structure is about 3 micron by 600 nanometer. These are the measurements. These are not simulations. The simulations look almost identical. And you can also see that this mode here has a line width of 2 delta H equals 280 microtesla. So that means delta H is 140 microtesla. So indeed, we have a very narrow line width in this case. And even the reason that the damping is relatively large with 2 times 10 to the minus 4 is only that the inhomogeneous broadening is extremely small. So the inhomogeneous broadening is 75 microtesla, so less than an Ørsted. Okay, we can also do other structures. So here you can see a kind of drum resonator. These are also modes measured in this resonator. And we can also have these kind of mushroom structures where now we're trying to couple light into them to get something like circulating modes that can couple to magnons. And we are also looking at mechanical oscillations. And I can say without showing any results that we are quite successful in this case, but not we, but Grégoire de Lubin. But anyway, so we also have a possibility to transfer this because, as I said, we cannot do superconducting resonators on a GGG substrate, and these structures are still grown on a GGG substrate. But we can make larger structures like this, which we call the centipede. And in principle, we can cut something out and simply place it somewhere else. And this is again measured with MOG, so you still have nice resonance properties, but you have to use a few tricks. Anyway, in the gist, we can take YIG and we can put it somewhere else, and we can make small YIG structures and we can put them onto something else. And now what we wanted to do, so this is the structure that we transferred. Actually, this was simply cut out of a film, but still it's very high quality. So you see this is 8 by 7 micron. It's not super small, but it's definitely already very small. And Philip Geyer designed a resonator which basically looks like this, where we wanted to concentrate the field here in the center. As you will see, this works nicely. It works way too nice. So this is what we get. So this is when we have what we say the easy axis, so that we have the magnetic field. Let me just switch back, that we have the magnetic field along this direction, and the hard axis is if we have the magnetic field along that direction. And you can see that for the easy axis, we have this kind of huge splitting with something going on here. And for the hard axis, we also have some splitting. And in principle, you wouldn't expect any resonance there, but this is a question of the geometry. And you can see that you have multiple spin wave modes that all present a pretty strong coupling. So we did not calculate whether they have really strong coupling. And we did an estimate with a line width for the YIG of 11 megahertz, but you will see on the next slides that this estimate may also be wrong. But if you look at the delta omega of the cavity, which was about 1.3 megahertz, then G over 2 pi is 53.8 megahertz. And this means that we're definitely in the strong coupling regime, and we calculated the coupling per spin of 63 hertz. And we used a saturation magnetization of 140 kiloamps per meter.
So Georg, quick materials question or two on your structure. So first, the hard and easy, is that just shape anisotropy, or do you have some crystalline orientation with respect to the cut directions?
You mean because I'm talking about a hard and easy axis?
Yeah.
No, as I said, the hard and easy axis is just our definition of the direction of the magnetic field. There is no anisotropy in the material. So it's just that we wanted to talk about one axis where we have nice resonances and one axis where we have where we have bad resonance. So don't confuse this. It's not a magnetically hard axis and soft axis.
Thank you.
So
And then the second question, do you do any additional annealing or treatment after the fib cuts?
no.
Thanks.
So the cooperativity, by the way, in this case is about 202, which is, I think, a nice number. So, but still where we would expect the so-called, in principle, uniform mode. You can say if you have a microstructure like this, there is no uniform mode anymore. there is just a zero node standing spin wave. So this is something that you have to deal with. And in principle, there are even two, because you can have a zero node Damon-Eschbach mode, and you can have a zero node backward volume mode with the same field direction. And theoretically, there can be a split. And it may be that the small split that we saw for the bridge was this splitting between the two. But it doesn't matter too much here, because here we have something which looks huge. So a very broad gap, and apparently there are some features, and we tried to calculate this for a long time together with Michael Flatte, and finally we came up with a different idea, because so it's a very low damping material and it's a high Q resonator, or not a high Q resonator, it's a very good resonator. So these are simulations by CST Microwave Studio. And you can see that indeed we have a very small spot in the center where we have concentrated all the field. So we feed the resonator gets on resonance, and when it's on resonance, this field immediately becomes pretty strong, and it couples to a high Q YIG structure. So we have a very small mode volume, very nice mode overlap, and we have an extremely high H field at the sample location, and this simply could be too much. Now, let me switch. So these are now MUMEX simulations where Seth calculated the modes in our structure at an excitation field of 8 microtesla. And you see that where you would normally expect the uniform mode, you have a multitude of modes, many of them perpendicular standing spin wave modes. So these are different layers in our structure. So this is the slab outline, and these are different layers in the slab, and you can see that they even behave differently. And depending on where you are, at least you have a mess of multiple lines. Yes?
Thanks for sharing this data. I potentially missed the point that you want to make. So are you in the limit where you go beyond the Walker breakdown and you're exciting nonlinear excitations in the yttrium iron garnet due to the field concentration, the field enhancement, and the large amplitude? If this is the case, then if you dial down your microwave input power, you should end up with a reduced set of modes. So is that what you're saying, or is it something different?
This is what for the moment. So we should certainly discuss this. For the moment, we just have these simulations which show us that over above a certain microwave field, you get this. You can also see this simulation. This is a simulation for an excitation field of 0.5 microtesla, which is much smaller, and you see that here you basically have something which looks like a uniform mode. But the physics behind this, I'm happy to discuss this. Yeah, Greg?
Just to put it in my own reference frame, what kind of excitation powers at the resonator are you applying? So just
next slide.
Oh, okay.
Next slide will tell you.
Yeah.
So this is, again, the field. So for 0.5 microtesla, you have something like this. And already at 1 microtesla, it becomes more complicated. And above this. So we can go down at the moment to minus 90 dBm at the feed line. But so even at minus 90 dBm, things basically still look the same. We're almost at the detection limit, and Seth did the calculation. So we did all this, these CST simulations to see what excitation field we actually get. And even at minus 90 dBm, we are still in the regime where you would expect a nonlinear excitation. So, and that's why if anyone can work at lower power, so Hans, maybe you are interested to do this. So it would be quite interesting to see what happens if you go down there, but we cannot go down there with our equipment at the moment. And yeah, so there's a call at the call.
Related question. So you know the threshold power. I actually don't use this chair. It's not really connected to the ground. I figured out yesterday.
Yeah.
It's the fixed reference frame that you want to have. The question I have is, so are you already in a regime where you unavoidably are in the nonlinear excitation scheme if you consider the vacuum fluctuations of your microwave resonator? Or can you really dial down the power and should get to the linear regime?
I think we should be able to dial down to get to the linear regime. But as I said, we are at the very beginning here, and we are happy that we now understand that we are in the nonlinear regime. How we can get out of this is a different question, and maybe even going to low temperature may help in this case. And as I said, we're only working at 1.5 Kelvin, and if you can go to microkelvin, maybe this even helps. Okay, but now we know.
Just
Yep.
one quick question related
Yep.
to your like 2 slides before. I think the slide number 55. Yes. So here I can see like some vertical lines around like 45 millitesla, where there is this avoid crossing.
you mean?
Exactly this one, and you can also see like more tiny ones on the
Yeah, yeah.
right hand side. Yes,
Yeah.
I'm just like wondering whether you guys have thought about the origin of these vertical lines.
It's actually, in principle, it's in the simulations, because you can see that we not just have a very broad resonance line, but we have a multitude of lines. So this, here you can see, so this is, in principle, what you have there. And I would guess that probably the biggest of the largest of these peaks, they give you just additional anti-crossings there, because every spin wave that you have in this structure, it gives you an anti-crossing, and there you simply have nothing which goes down to zero anymore. So
But it looks like these lines are kind of like vertical and
no,
do
it's not
couple.
vertical. It's slightly bent.
Okay, so they have like
yeah.
some curvature. Okay.
Yeah, there is some curvature. Yeah, that's why we also try to model if this might be, so you can see it goes basically like this, if this might be a way to calculate the strong coupling. Ah, there's a question over there.
I wasn't clear on the experimental setup, but do you use a cryogenic amplifier on the readout?
No, we don't have a cryogenic amplifier.
I think if you used a low noise cryogenic amplifier, you'd be able to get a much better signal to noise at that
Yeah,
temperature.
for this, I mean, our setup is very simple. It's a cryostat with a VTI and a magnet, and to get a cryogenic amplifier inside, we really have to modify it. And at the moment, we're happy that we can do some measurements. And I must say, for this kind of stuff, I merely rely on people who can do this much better than we can. Our manpower is very limited, and so to modify the setup and maybe not being able to do some measurements for some time is, for us, it's not a good idea at the moment. But certainly, it's a good plan. So now,
just one more question related to this like non-linear. This is something that interests me, and I'm just like wondering, how do you guys how do you guys define where you have non-linear regime and where you have linear regime in terms of both like experiment and micromagnetic simulation?
we define the linear regime where we actually have the uniform mode where we would expect it, and we can see the uniform mode and no other modes. And when suddenly a lot of modes appear in the same place where before we had only one, this is what we would define as the nonlinear regime. It may be a very simplified definition, but for the moment, this is what we have to fight. So now we come to the other stuff. What if you have two magnets and one resonator? And actually, there are two possibilities. You can couple two ferromagnets to the same resonator, and you can also couple two magnets through the same resonator. And what can you expect? You could expect maybe coupled magnon states. You could expect bright state, dark states, strong coupling, weak coupling. And what we need for this, we need two magnets that we can independently tune in resonance frequency. And useful also is if you have a separate excitation and detection for the respective magnets. You will see the first, we can realize the second one not. and the coupling of each individual magnet to the resonator must be there. And there are two experimental examples, one from the Hoffman group and one from Shufeng Zhang's group, so he was a co-author at least. I don't know whether it was done exactly in his group. And in this case, there was separate control of 2 Higgs spheres, so we had separate antenna and separate field tuning for 2 Higgs spheres in a resonator like this. So this was a superconducting resonator, and this was a cavity resonator, and Shufeng Zhang showed dark states in a common cavity, but with separate field control, so you could control the resonance field separately. And what we had in mind, actually, it was just a wild idea. We said if we have 2 magnets that we can independently tune, there is also this effect of weak coupling, because if you have 2 oscillators weakly coupled with almost the same frequency, they tend to synchronize. And we were wondering whether this could also be demonstrated with magnets in a resonator. Could be that it's impossible from the point of view of physics, but the idea was there, and we said, let's do the experiment. So this is just an example. So this is for spin torque oscillators, so nothing with something with magnons, but not with superconducting resonators. You can see you basically have 2 oscillators, and once the frequency comes closer together, it makes a zip, and then you have just one very narrow line. That's another effect of the synchronization. The line becomes more narrow, the line becomes bigger. And only when you go far away from this resonance frequency, then they split again. So, so as I said, what we need are 2 magnets with independently tunable resonance field. And we thought about using the shape anisotropy field. I mean, from our first experiment with permalloy, we knew that we can actually, by using the right angle, we can tune the resonance frequency. And so we put a permalloy stripe on a lambda half resonator, so that's a pretty big one. And then we rotate the magnetic field in the plane of the resonator. We have one of these nice vector magnets where we can do this. And here you can see at a certain angle, so we start with an angle theta, 25 degrees. You see we have this anti-crossing, and it moves with the angle. And actually I told Anoop, who did the experiment, so you just measure how much angle do you need to have 2 completely separate anti-crossings. Because I said if you just try to tune the 2 anti-crossings on top of each other, you cannot show anything. You want them separate, but you have to be able to overlap them or to put them right on top. So for identical frequencies, the shape anisotropy increases the resonance field when the field is applied away from the easy axis. And it seems like 50 degrees are enough to completely separate 2 coupling regimes around the uniform FMR modes. So let's make 2 stripes at an angle, and we will be able to tune from separate resonance fields through identical resonance fields and back to separate again. I see I have to hurry a little bit, but there were already questions asked. Just a few words about resonators, because in the end, one thing will become important. So lambda half resonator can be coupled capacitively at both ends. Our LC resonator is typically coupled inductively on one side. That's a big difference, because if you have a small capacitance, you have a small transmission for any given frequency. Larger capacitance leads to bigger transmission for any given frequency. This is also valid for the resonance, but also the problem is if you couple nicely to the environment, so you can do an easy measurement, it also means that you have a loss path for your resonator. So in principle, you want your resonator completely isolated, and the Q factor is maximum when you cannot see it anymore. So if you have smaller capacitance, you get smaller signal at the output for background and resonance, but you get a pretty sharp resonance. So what you see, this is your input and this is your output, which gets already very small. If you have larger coupling, you get a broader resonance and you get more signal at the output. For the LC resonator, small inductive coupling gives you small damping of the output signal. Larger inductive coupling leads to a larger damping of the output signal for any given frequency. Because you have the feed line and you damp the signal in the feed line by what is absorbed in the resonator. So it's a different effect. And Same thing if you have a small damping, you have a sharp Q factor, but you have a very small dip here in the signal. And if you have a stronger coupling between feedline and resonator, then your peak gets a bit wider and you also see a bit more of it. So, okay, that's brief introduction. Now this is a lambda half resonator, capacitively coupled at both ends. And we have two polymer stripes with 50° in between. And I briefly want to introduce you to some special modes or some special geometries that you can identify, because so if you apply, so green is the external field, this blue arrow is the RF field as it's produced by the resonator. This is the magnetization direction, and this is the component of the RF field with respect to the magnetization. So here you have the same magnetization direction, and in principle this is completely symmetric, so you would have the same resonance frequency for both. However, you see that the RF field has a 180° phase shift in this case. This case where the external field is in this direction also, it's not as obvious, but it's also the same. You have the same relative angle with respect to the magnets, and in this case you have the same phase. So you would also expect the same resonance field. So keep in mind 90° and 0, 180 should give you resonances on top of each other. Then there is another special case when the magnetization is along one of the stripes. In this case, you have a large excitation field here, and here you have a different resonance field, and you also have a very small excitation field with respect to the magnetization. And at 40 and 130, so they all appear symmetrically for both stripes. Here you have the magnetization perpendicular to one of the stripes. And theoretically, you have no RF excitation field in this case, because the RF excitation field is perpendicular, is parallel to the magnetization, so you would expect this resonance to vanish. So you would not even see different positions, you would just see that there is one resonance left. So now comes the fun part. We start 180° is when we had the field in the, where you would expect identical resonance frequencies. So we just did 5° steps. So now you see there is a second one appearing. And now they're moving together when we come to the 90° state. Actually, 85° is the one where I think where things are happening, where we're exactly perpendicular. There was a small misalignment. And now we're going back. Again, two resonances are appearing. We did not do a detailed analysis whether we have anything like weak coupling or synchronization in this case, because it's very difficult to determine. But there's another thing. I mean, you may have realized before that when I showed you the single permalloy stripe, you just had the resonance and you had the off resonance part. And the resonance was dark and the off resonant part was basically orange. Now you have these features here. These features are about 30 dB below off resonance. It's actually at the measurement limit of our VNA. So there, at these points, these are very sharp points, and at these points there is no signal going through the resonator. And that's why I showed you this before. So these are dips, and they're so they're relatively large. I mean, we are at low intensity, but still we're going down much more, and we cannot explain the origin of these dips. I mean, that's why I showed you these resonators. If you have a capacitively coupled resonator, anything which happens inside the resonator is seen at the other end. And if we don't see anything there, this means there is nothing going on in the resonator. We are feeding the resonator, and there is nothing arriving at the other end. To have something like destructive interference, you need something to arrive there. So it's I have no idea. And here you can see also the order of magnitude. So we did some line cuts through one of these blue spots. And these are logarithmic cuts, one in field space and one in frequency space. And you can see that in field space, the width of such a thing, full width at half maximum, is difficult to define for a dip on a logarithmic scale. That's why I also had a linear plot. There you can at least talk about something like a full width at half maximum, although the physical meaning is not really clear, but you can see that the width is less than 2 millitesla in field space, and it's less than 20 megahertz in frequency space. And to give you an idea, typical resonance for permalloy would be 6 millitesla line width and maybe 200 megahertz. So there are two questions, one there and one there. So if you know any artifact which could show what we are seeing, I'm happy we don't make fools out of us.
So did you consider dipole-induced reflection? So this is a quantum optical effect that you get whenever you have a two-level system in a cavity. If you shine light right at the resonance for the coupled two-level system coupled to the cavity, then you end up with these dips. They're often not visible because they're very narrow.
We did not consider this, otherwise I would mention it. So let's discuss this. We are really interested in every possibility which might explain what we're seeing here. So there are more maybe suggestions, I hope.
So is there, I mean, I appreciate the argument about if there's nothing comes out of the cavity, there must be nothing in the cavity. What if what if something small is coming out of the cavity and there's some sort of small side channel and the two are cancelling each other out?
It would have to be really small because, as I said, we are 30 dB below the off-resonant case.
Yeah. Yeah, anyway. I mean, the fact that it goes to zero suggests that, to me at least, that there's two things cancelling each other out, right? And
yep.
Yeah. And if you have some sort of pickup that goes from your input to your output without going through the cavity, that might be a way to...
That's certainly, we've been thinking about things like this, but what's surprising for us, and that's where we don't have an explanation yet, is, I mean, it moves with a ferromagnetic resonance. So it has to do with a ferromagnet. Otherwise, if it were just about the cavity, I would expect it to remain in the same place. But in this case, it really moves with the resonance. So it has to do with the magnetism. As I said, if it's an artifact which can be explained, I'm still happy, because if it has to do with the magnetism, it would still be interesting for us. So.
Okay, recently we found in just microwave resonators, we could induce electromagnetic induced absorption when we had an extra degree of freedom with more than one system. And you have to get a balance correct amplitude and phase. So it's like an interferometer. And when you did that, you could get this on resonance dip with a slope more than an order of magnitude higher than the Q factor. But it's always a dip, it has to be a zero.
Okay.
So I think it's an effect like that, some sort of electromagnetically induced absorption or the magnetic system. So there must be some phase shift involved where you get a cancellation, but it's a resonant type cancellation.
Yep. Okay, I hope that we can discuss this during the next days, because that's exactly what I was hoping for, that people know some stuff that we don't know and that we also don't find in the literature so easily. So Zeke has another question.
So apologies that this is a restatement of something already said, and I'm just not following all the implications, but I wonder, looking at the shape of your line, thinking about just from the microwave perspective, propagating through that system, you're going to have effectively a change in index when it passes through the region with the magnetic material, and so that will depend on the magnetization. What that change is. I wonder if you're maybe getting lucky with setting up some standing wave in between the two bars or within the length of a bar or something like that in a certain condition that's giving the kind of cancellation
Yep.
that people are bringing up.
Yeah, I've been thinking also about something like a Fabry-Perot resonator, but this gives you a large transmission at one point and not a dip at one point. There's even one more comment from Hans.
So there was an extensive discussion in the field of optomechanics about absorptions and transmission features. And for these microwave systems, so if I recollect this correctly, it just depends on the setting. So you can, so everything happens inside your cavity. And what I want to say is it depends if you're using this hanger type, reflection type, or transmission type resonator. And depending on that, you will give the interference which give a different result or a different signature, like a dip or a kind of nearly perfect absorption.
Okay.
And so these boundary conditions or the play a kind of important role in this entire treatment at the end.
Yeah. Okay, I hope we can discuss all this. Let me just go one step further because I also have to get to the end of my talk. So this is, by the way, this is the resonance of the resonator, just to show you that it's about the same order of magnitude. So line cut of the resonator shows a full width at half maximum of about 10 megahertz. And yeah, so this in principle has already been said. And one idea was also whether somehow we may kill the superconductivity, but it's not permalloy FMR in this case. And it only appears in our case for 2 permalloy stripes. For the 1 permalloy, we haven't seen anything. I mean, if it's something like a special geometry, then it's clear that 2 permalloys may cause this. But also, please keep in mind that if we have 2 separate resonances for the 2 permalloy stripes, we have 4 of these features. So it's, and I really would like to explain this field dependence. So it shifts with a resonance field. And for each of the stripes, for just if we have a resonance, we always have a feature which appears here. But let's discuss this. I'm very interested to hear all this. And as a conclusion, so we can definitely get our superconducting resonators for strong coupling. And the pattern YIG offers new opportunities. But it's not easy to keep in the linear regime if we have this large mode overlap. And yeah, as I said, we have this puzzle with the 2 stripes. Maybe it can be solved at this conference. But let's also think about other experiments. So feel free to join the effort if you have any idea what kind of experiment could be done either with permalloy or with YIG. With such a superconducting resonator, we are willing to collaborate. And if it can be done without too much development, at the moment we don't have manpower to develop a lot of new experiments. But if there are samples that we can do, might be a good idea. And as I said, so there were already 2 people willing to do this. If you currently we are limited to 1.5 Kelvin. If you want to have a look at lower temperatures, it would certainly be very interesting. Okay, that was it. Thank you very much.
We might have time for 1 or 2 more questions.
Let me help you.
So I don't know if this addresses your fundamental mystery, but one thing that you didn't discuss is the 2 permalloy stripes having some common interaction, some common mode. I mean, they're just by rule of thumb, they're not that far apart that their dipole fields, are potentially interacting. Have you looked at that?
No, not yet. I must say, so we, for the moment, we simply try to get this phenomenon clear, and it actually took a while, just also because of problems with the cryostat, to get the full set of angle-resolved experiments. It took quite a while, and I said, let's first finish this set of experiments, and then let's go further, because if you want to have these roughly 30 different measurements, and in the end, 1 or 2 are missing, it's really bad. So what is this set complete? And now we can have a closer look. We will probably even need to do finer angle resolution around where the resonances are coinciding. But the large line width that we have also makes things a bit difficult.
So, and with full understanding that this is work in progress, so not meant as a criticism, and probably something you've thought about, but an interesting control might be to move one of the permalloy stripes, one period of your patterned waveguide further away and see.
We also have another resonator where we have a different angle between the 2 structures, and we are working on more resonators, but each resonator takes some time. So actually fabrication for us is much easier than the measurement. Measurement takes a lot of time, and probably if the next resonator shows something interesting, it will remain in the cryostat for another few weeks, and then we can measure the next one. I think at the moment we have something like 4 or 5 different resonators sitting down there, and other interesting experiments which may even make things easier, because we may be able to do the same experiment with YIG. So then at the moment we just use permalloy because it's so easy from the point of view of technology. And actually, I mean, Anoop is doing a very good job. He even managed to make the resonator, characterize the resonator, then put 1 permalloy stripe on the resonator, measure the resonator, then put the next stripe on the resonator. But yeah, lots of things to do.
Okay, really interesting talk, and thank you for sharing the new results. So you were mentioning synchronization, and the thing that popped into my mind, this is not exactly, this is a question, but only loosely. So Kan Ming, who has some nice work where they distinguish between kind of coherent coupling to a resonator and dissipative coupling to a resonator, where the magnetic material is kind of has a viscous interaction with the resonator. And there you do get synchronization, but not between the 2, like in your case you have 2 permalloy discs, but it would be like with the resonator itself.
Yep.
And given the nature of permalloy, and then you have these different angles where you're applying a magnetic field not along, I guess maybe permalloy doesn't have an even easy access in these films, but
it's just shape and
but you are misaligning. You're getting to cases, for instance, where the RF field is along the magnetization.
Yep.
Then you're going to get, and I'll talk about this afternoon. So normally we think in terms of the coherent XX coupling, where a displacement of the magnon causes a displacement of the resonator. And I'm wondering if you have considered XY coupling, where when in the perpendicular field arrangement, where what you're doing is you're modulating the frequency of the resonator, actually, no, I have to think about this carefully. But anyway, you get a term in your Hamiltonian that looks like A dagger A times B plus B dagger. So it's the optomechanical Hamiltonian. You can get that, and it may be something that can help explain these results, or maybe not. But okay, I'll talk about the optomechanical like Hamiltonian in magnonics this afternoon, and then we can have a discussion afterwards.
Yeah, there are certain effects that you can have. One of the effects is certainly you can also have parametric pumping, but that would be at 2F or at omega 1/2 of the pumping frequency. The other thing which you could have actually is that the permalloy stripe, if it's especially if it's magnetized along the resonator, you have a field component which cycles through the resonator, which can modulate the resonator frequency. Maybe this is what you're talking about, and this is but it's a similar thing to optomechanics, I think. But we didn't consider this, and in principle, as I said, we didn't do any calculations beforehand. We just thought this might be an interesting experiment. Let's see what we get, because it could be done so fast. And then we found this. If we get a nice explanation now, then we can move on to the next one.
Hey, Georg, I was wondering about whether you guys considered level attraction from non-Hermitian systems to kind of explain these features, because it kind of resembles a little bit and we don't see like a void level crossing there, but something that like resembles this level attraction. So I was just wondering whether you have thought about that.
No. Very simple for the moment. It just looks for us, if we move the thing, you have one avoided crossing here, you have another one there. So for the moment, if there can be something else, as I said, we're open for any suggestion that we can check. For the moment, we just try to find things like this in the literature, and at least for microwave cavities, we didn't find them. That's why I was presenting this here. So any suggestion is good, and I will probably make a list of papers that we have to go through in the end of the conference. And then hopefully we'll be happy in understanding what we have there.
If there are no further questions, let's thank our speaker again.
Oh yeah, so now we have the coffee break. Let's take it easy with